Rebeca Fischer from Harvard University will be presenting on axial and radial diffraction studies of Mg2SiO4 and iron silicon nickel alloys.
Thanks so much for the introduction. Thank you all for being here today. So I'm going to be talking about a couple of different projects that my group has been working on involving some synchrotron techniques, one using axial diffraction to look at phase relations of Mg2SiO4, and one using radial X-ray diffraction to look at deformation of iron silicon nickel alloys. And I just want to start by pointing out that these two projects are the work of my two more senior grad students, Junjae Dong and Matthew Brennan. Okay, so why do we study deep earth materials with synchrotron X-ray diffraction? As most of you probably know, it can give us a wide range of information, things like crystal structure, density or volume, which we can turn into equations of state, information about melting and subsolidus phase transitions, and a variety of other physical and chemical properties like deformation, strength, kinetics, chemical reactions, etc. Just one example of this from our earlier work and how we can use this to detect melting. This is some laser heating of Fe9Si alloy at 74 GPa. The X-ray patterns are color-coded by temperature, with red being the hottest. You can see that as we get hotter and hotter, some of the diffraction peaks in the sample disappear, and we get this nice diffuse hump in the background caused by the diffuse X-ray scattering of the melt. And of course, we're interested in knowing these things so that we can apply them to the Earth. Like, for example, to seismology and Earth structure, geodynamics, chemical composition, the formation and evolution of the Earth, and how all these things work in other planets. And again, just a quick example of this from some of our earlier work. We had measured equations of state of several different iron silicon alloys, and then used them to make this figure, which is showing density as a function of pressure over the PT range of the Earth's core. So the colored curves are our different iron silicon alloys. This black curve is PREM, the seismologically determined structure. And you can see that PREM falls sort of in between our different alloys. And so we can interpolate and find that we can match the density of the outer core the best with about 11% silicon. So that would be if silicon were the only light element, so it's an upper bound. So for the sake of this talk today, we're going to be focusing on a subset of these, specifically subsolidus phase transitions, deformation and strength, to learn more about seismology, Earth structure, geodynamics, seismology and Earth structure, and formation and evolution of the Earth. Okay, so as I mentioned, there's going to be two parts to this talk. Part one is using axial X-ray diffraction of Mg2SiO4 to better constrain phase boundaries in the mantle transition zone. This is very much a work in progress, so all of the numbers I'm going to be showing you today are somewhat preliminary. And then in part two of the talk, we'll be discussing radial X-ray diffraction of iron silicon nickel alloys to understand the effects of silicon on the strength of the inner core. And that work is published, but to some extent still a work in progress as well. Okay, so for part one, this project is led by my now fifth-year PhD student, Junjae Dong. Some quick background. Mg2SiO4 is force-stratic olivine in the upper mantle. It transforms to wadsleyite and then ringwoodite in the transition zone before breaking down into bridgemanite plus periclase in the lower mantle. You would think that a mineral that's so abundant in the Earth's mantle is something that, we would know its phase diagram extremely well. And we do, but we don't quite know all of it. So this is a summary of some of the literature results on the pressure temperature phase diagram here. The light blue is wadsleyite, dark blue is ringwoodite, and the green is bridgemanite plus periclase. These four sets of black lines are phase boundaries proposed by these four previous studies, and the squares are the experimental data that underlie these four studies. This green curve here is an example of a geotherm for modern day Earth with a potential temperature of 1600 K. And you can see that a lot of the experiments we have in this system are below or around this geotherm. And if we look, say, a few hundred degrees hotter, there's fewer data. The data don't agree with each other as well. There should be a phase boundary from wadsleyite to bridgemanite plus periclase at high temperatures, but it's the slope of that transition is virtually completely unconstrained. So it's important to understand these kinds of phase boundaries to understand the thermodynamics of this system and more complex systems, to compare to seismic discontinuities, and to estimate mantle temperature and its variations. So we set out to do some experiments to try and fill in this phase diagram a bit better, specifically focusing on the high temperature region. We did this using a laser heated diamond anvil cell. So our samples were mixtures of synthetic Mg2SiO4 plus tungsten, which acted as a laser absorber and pressure standard. And we loaded that in between layers of KCl, which acted as another pressure standard, a pressure medium, and a thermal insulator. And we put that in a rhenium gasket, compressed it between two diamonds to reach pressures of something like 18 to 26 GPa, targeting the transition zone. Heated it from both sides with an infrared laser to reach temperatures of up to about 2600 Kelvin. And we did these experiments with in situ axial X-ray diffraction at the APS, both at beamline 13 IDD GSE cars and 16 IDB HP cat. So in this axial geometry, the X-rays come in along the compression axis, and then the diffracted X-rays come out the other side. So we looked at 6 experiments this way. We did 1 to 3 laser heated spots on each experiment. So I think we got something like maybe 12 heating cycles in total that we used. This is an example of what some of our X-ray diffraction data look like. This is 3 patterns taken from the same sample, the same heating cycle at 3 different temperatures. So on the bottom is the coldest pattern. The peaks marked with light gray and dark gray are from the KCl and the tungsten. The peaks marked in dark blue are from ringwoodite. So in this pattern, we just see ringwoodite, so the phase identification is fairly straightforward. As we increase the temperature, we start to see new peaks come in that are marked by these light blue rectangles. That's the appearance of wadsleyite. And you may notice that some of the ringwoodite peaks did not fully disappear. And that's because there are some slow kinetics in this system, and you get a lot of metastability. So what we did was we only used data we collected on heating, and we used the appearance of the new phase as a sign that we had crossed the phase transition. Finally, as we go up to this 3rd pattern at the highest temperatures, again, some of the wadsleyite peaks persist, but we now get these big green peaks coming in that are from the bridgemanite. So that's how we go through and sort of analyze a series of diffraction patterns to assign phase stability to them. And this is what some of our data look like in PT space. This is just 2 example heating cycles that I'm showing here. Pressure, temperature, space. The gray phase boundaries in the background are the same 4 that I showed on the previous slide for comparison. And one point I want to make here is that comparing between studies, it's really important that you consider what pressure scale you're using. So Hirose 2002 did some careful looking at where the triple point is, and he used a gold pressure standard. We recalculated his triple point using 2 different gold pressure scales from Anderson and Jameson. And that gives you either this red triple point or this green triple point that are maybe 2 or 3 GPa apart from each other. So it just sort of underscores you have to be careful with what pressure scale you're using, and at least be consistent between studies. However, we will note that the pressure scale you use does not tend to significantly affect the Clapeyron slopes of the transitions. So then we put together a compilation of literature data to combine with our new data set. We gathered 317 data points from 9 previous studies listed here. Our criteria for choosing these data, one, they had to come from temperatures of at least 1400 Kelvin. This was partly to avoid the even more sluggish kinetics and metastability problems that happen at lower temperatures, but also because you have Akimotoite and other low temperature phases coming in at some of these lower temperatures that are going to affect the phase boundary, and they can be very difficult to detect due to their narrow stability field. So we wanted to just avoid those. We also only use data obtained on heating, again, to avoid this problem of metastability. We could look for the first appearance of a new phase. We used data from both diamond anvil cell and multi-anvil press, but it all had to have in situ synchrotron X-ray diffraction so that there was an in situ X-ray pressure standard. And we did that so that we could then correct all of these data to a common pressure scale. We used the equation of state of KCl from Duvall et al. 2012. And for experiments with different pressure standards, we used other equations of state that have been cross-correlated against this Duvall et al. Equation. So they should all be sort of self-consistent at this point. And then in terms of actually turning these data into phase boundaries, we used a logistic regression method. This is a sort of maximum likelihood estimate for the phase boundary location based on the experimental data, and it's an unweighted procedure. So in this example, we're looking at the phase transition from ringwoodite to bridgmanite plus periclase. And this is approximately isothermal data that I'm showing you here from about 1600 Kelvin over a range of pressures. So the data span different pressures, and this vertical axis is the probability of observing the phase transition. So where we see ringwoodite, the probability is 0. Where we see bridgmanite plus periclase, the probability is 1. And of course, these are real data, so there's some overlap here. So what the logistic regression fitting does is it fits this solid black curve that tells us how likely it is that the phase boundary falls in this range. So we take the phase boundary to be where the probability is 50%, which is this red line here, which gives us a phase transition pressure of 24.1 GPa. And then we can estimate the uncertainty on that by considering the interquartile range. That is a P from 0.25 to 0.75, gives us an uncertainty in that pressure. And so we do this simultaneously at a bunch of different temperatures over all 3 phase boundaries to construct the phase diagram. And this is the big result. This is the phase diagram we've put together. So all of the little squares that you see are our literature compilation of data. The circles you see are all of our new data from this study. And then the colored shading in the background is the phase identification from the logistic regression. So these are the phase boundaries that we found. And you can see it does a pretty good job, and it at least gives us some kind of slope for this Wadsleyite to bridgmanite plus periclase, although it's still less constrained than the other phase boundaries. Interestingly, we also calculated the phase diagram of Mg2SiO4 using Hephaesto, a thermodynamic code, and that's this sort of dotted black boundaries you see here, which are a little bit of a different shape than what we see in the experimental data. And we think that might mean that experimental database from 2011 needs to be updated with some of these newer data sets. So that's something we've been talking to Lars Stixrud about. And here, I've just removed the data points themselves from that figure, so you can still see the stability fields. And now these dashed lines here are the uncertainties on the phase boundaries that we got from those interquartile range on the logistic regressions. And finally, we put some effort into getting the best constraints we could on the Clapeyron slopes of these 3 phase boundaries. We did this using this logistic regression with bootstrapping. So we took our literature compilation combined with our new data set, and we resampled it with replacement 10,000 times and used that to produce these sort of histograms of most likely slopes for these three different phase transitions. So for Wadsleyite to ringwoodite, we find about 3 MPa per Kelvin. For ringwoodite to bridgemanite plus periclase, we find about -4 MPa per Kelvin. And for Wadsleyite to bridgemanite plus periclase, which was previously not really constrained, we get -1/2 MPa per Kelvin. And again, if you don't like our choice of pressure scale that we used, these numbers here with the Clapeyron slopes are not very sensitive to that. So this is more robust. Just some summaries from part 1 of the talk. Despite many previous studies on Mg2SiO4, this high temperature transition was poorly constrained. So we did axial X-ray diffraction in a laser heated diamond anvil cell to look at that. We combined with a lot of literature data and corrected everything to a common pressure scale, used a logistic regression to fit the phase boundaries, finding these 3 slopes for the 3 transitions. In the future, we have collected some preliminary data on Mg2SiO4 that we have yet to look at. We're also hoping to collaborate with Lars Stickshard on updating their thermodynamic database with these new data, so that we can actually look at what this would mean for pyrrolite. Because of course the mantle is not Mg2SiO4, it's a much more complex rock. But having better data on these kinds of end members let us make better predictions for pyrrolite. Okay, and so now we're going to dive into part 2 of the talk, which is radial diffraction of iron, silicon, nickel alloys to understand the effects of silicon on strength. And this project is the work of my student Matt Brennan. So the Earth's inner core contains a few weight % light element, possibly including silicon. It also probably contains a few weight % nickel. It exhibits seismic anisotropy, meaning that sound waves travel faster in the polar direction than in the equatorial plane. It also has some other complex features that I'm not going to get into. Its anisotropy is thought to be caused by preferential alignment of HCP-C axes with the Earth's rotation axis. A lot of mechanisms have been put forth to explain them. This might have originated in the crystallization of the inner core, or it might have happened afterwards, for example, due to solid state convection, translation, or electromagnetic forces. These different kinds of mechanisms are compatible with different iron alloy strengths and depend on texturing. So it's generally helpful to measure the strength and texture of different alloys so that we can say, if we can narrow down the inner core's composition, we can narrow down the mechanisms that might have formed it. And there have been a few previous studies looking at the strength of iron and iron alloys. Gleason and Mao in 2013 determined that an iron inner core is rheologically weak. This is their figure in the upper right. So they're showing this. It's basically a strength versus temperature at inner core pressures. The strength of pure iron is, according to them, only a few GPa. Merkel et al. In 2013 also looked at iron. His extrapolation works a little bit differently and gives a slightly higher strength for pure iron in the inner core. And then Reagan et al. 2018 found that the addition of 5.5 weight % nickel would increase the strength by about 25% at inner core conditions. So the results of these studies are kind of summarized in this figure below, showing the strength as a function of temperature at the inner core boundary and inner core center. So there's some disagreement even over what the strength of pure iron is, but it's all fairly low at these kinds of high temperatures. It's on the order of 1 to 10. Notably, to our knowledge, there was no previous studies that have measured the strength of an iron light element alloy before. So we decided to look at 5 different iron, silicon, nickel alloys. So these alloys have between 5 and 10 weight % silicon, and 0 to 6 weight % nickel. They were either powders or foils. We loaded them with a piece of platinum to serve as the pressure standard and no pressure medium to maximize deformation. And we compressed these in a diamond cell up to about 60 GPa. Most of these we did at 300 K, although we did one preliminary laser heating experiment that I'll mention later. And we did radial X-ray diffraction at the ALS beamline 1222. This is just a schematic diagram. Basically, the idea is that the X-rays come in from the side. You use an X-ray transparent gasket. And so now the diffraction is happening perpendicular to the compression axis. So you see the highest possible stress. Here's an example of what some of our data look like. These are caked images, meaning they've been sort of unwrapped. So we're showing 2 theta versus azimuthal angle. These were both taken on Fe5Si5Ni. The one on the left is from 6.5 GPa and shows the BCC structure. The one on the right is from 30 GPa and shows the HCP structure. The sinusoidal distortion of the rings indicates the elastic deformation, and the intensity variations within the rings indicates the plastic deformation or texturing. So we take each of these patterns and run them through an elaborate refinement to extract all kinds of information, including the strength. Specifically, we're extracting QHKL, which is the elastic stress resolved on a specific diffraction peak. And we want to be able to relate the deviatoric stress on the sample, T, and the average QHKL across all of the peaks, which we abbreviate Q. And if you make some simplifying assumptions, you can come up with this equation, T equals 6GQ, where G is the aggregate shear modulus. And you can equate T to yield strength if the sample is plastically flowing and the peaks are exhibiting their maximum Q. So in order to sort of get at what the strength of the inner core should be, we need to know the effects of both pressure and temperature on both G and Q. So we get dGdP from a fit to Enrich's literature data from these studies. We get dGdt from a fit to Prem inner core shear velocities. dQdP is the main thing that we're getting out of our data, which is what's shown in the figure on the right. So the 5 different colors are our 5 different compositions. The different symbols are different measurements we made at different pressures. This is Q as a function of P. Initially, we tried fitting each composition separately, and we extrapolated them to the inner core, and this is what we found for Q. 4 of them were completely indistinguishable. One was a little lower, but still overlapped with an uncertainty. So going forward for the rest of this talk, I'm going to be using results from a fit shown by this black line, which is just a fit to all of the data, since they all seem to be fairly consistent. And then we also need dQdt, which we estimated from our 1 laser heating experiment, although that's something we'd like to follow up on later. So here are our results for the alloy strength in the inner core. Again, this is T, or the yield strength, versus temperature. The solid lines are the inner core boundary, and the dashed lines are the inner core center. So this is what I showed you a few slides ago, the previous studies on iron and iron nickel. Now these are the lines for our iron silicon nickel alloys. So we can see right away that silicon makes iron nickel alloys significantly stronger. It's something like a 1 order of magnitude difference. Initially, we were concerned that this might have been some sort of methodological difference or something like that. So we went back and we did another experiment on pure iron, and we made sure that we could reproduce these earlier studies, and we could. So it really is a real difference caused by the silicon. And one of the reasons this is interesting is because we want to understand if the inner core deformation is dominated by diffusion creep or power law creep, because diffusion creep is not good at generating anisotropy. And so if the inner core is in diffusion dominated regime, that may suggest that anisotropy forms during crystallization and not after. So we can do some calculations based on this new strength we found for iron silicon nickel alloys. It implies that dislocation velocities and strain rates in silicon bearing alloys are about 1 order of magnitude lower than in iron nickel, and viscosity is about 1 order of magnitude higher. We also calculated critical grain size as a function of differential stress, which is what's shown in this figure here. We calculated the boundary between the diffusion dominated and dislocation dominated regions after Riemann et al. 2011. You can see that silicon has only a minimal effect on where this boundary falls, at least calculating it in this way. And fundamentally, the actual stress state of the inner core is just way too uncertain to be able to say which side of this boundary it falls on. These shaded regions are examples of estimates from a couple of previous studies. You can see they're all over the place.
1 minute.
So to summarize, several previous studies on the deformation of iron nickel, but no one had really looked at light element alloys before. So we did radial X-ray diffraction on iron silicon nickel alloys, combined with literature data on G to extrapolate strength to inner core conditions. The main finding is that silicon increases the strength by about an order of magnitude. In the future, we have beam time to do some more laser heating experiments to better understand the effects of temperature on all of this. And we're also hoping to do some experiments to higher pressures so we don't have to extrapolate so far. I'd like to just end by acknowledging primarily JJ and Matt, who the leads on these projects. Here's their email addresses if anyone wants to email them any comments or questions. But also, of course, our other co-authors on this work, other people who helped out the facilities we worked at, and various funding sources. I think I will just leave you with this slide. Thanks.
Thank you, Rebecca, for that great talk. Looks like we have one question so far from Shankarado.
Yeah, I have question or comments about the later part of your presentation about the strength of the inner core. So number one, very, 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 very important concept in plastic deformation is that there are different mechanisms for plastic deformation, and in the different regimes, mechanisms, even temperature or pressure sensitivity are different. So if you are in a wrong regime, you cannot even extrapolate. So I don't know at all, how do you go from your room temperature experiments to the inner core?
So to extrapolate in strength, there's a formalism. I didn't put the equation in here, but it involves you have to know Q and its pressure and temperature dependence, and G and its pressure and temperature dependence, like G naught. You also need an equation of state. There's a number of things you need to go in there to do the extrapolation. I tried to sort of gloss over that.
No, that is not extrapolation. The I can tell you one thing. For example, dislocation diffusion creep. Diffusion creep grain size sensitive. Dislocation creep is not sensitive, so you cannot extrapolate. So at room temperature, I'm pretty sure you're looking at the like a pile stress, and pile stress is nothing to do with diffusion, nothing to do with the high temperature plasticity. So even you cannot extrapolate. So that's you have to understand when you do those experiments to ask some question about the inner core. You have to choose the conditions where you can explore the plausibly dominant mechanisms happening in the inner core, and then you can extrapolate within that regime.
Yeah, well, ideally we'll be getting some more higher temperature and higher pressure data, so this won't be as big of a problem.
Yeah, thank you.
Well, we can take one more quick question from Zachary Gabel.
Hi, Rebecca. My question was about the, why do you say that by determining the transition from ringwoodite to, so the post-Spinel transition, say, on heating only, avoids metastability problems? Because I would have thought that the ringwoodite could be metastable too during heating.
The ringwoodite is metastable, yeah. So if you only look at data on heating, you start with, say in this example, just ringwoodite.
Yeah.
And then you heat it up and you see ringwoodite and bridgmanite and periclase. And that tells you you've crossed the boundary.
But you might have overcrossed it, right? You
might have, yeah. So we go really slowly and we take small steps and we sit there for a while. But then if you crossed over it, you probably still have some ringwoodite around. So if you tried to go back down, you'd never know when you crossed it.
Okay, because the tails of the X-ray hit the cold, unconverted ringwoodite. Is that what you're saying? It's like history.
It could be that, or it could be that it's just really slow at these temperatures.
Okay.
Yeah, I was also going to quickly ask about the time of how long you heated to form the bridge mud. It seemed like there were just a few peaks, and I wondered if you played around with how long you heated or to what extent.
Yeah, we did definitely try to go slowly and sit and collect lots of patterns sitting at the same laser power and stuff like that. I don't remember offhand exactly how much time we spent sitting there, but when we knew we were getting near the phase boundary, we did make an effort to do that so that we didn't just overshoot.
Awesome. Thank you, Rebecca.